About 400 years ago, when Galileo looked at Saturn through his handheld telescope, he actually thought at first it was a very strange object. He could see the rings, but he didn't know what they were, and it looked like a face with two ears on either side.
400 years later, in 1997, NASA launched the Cassini spacecraft on a mission to Saturn, allowing us to see it like we'd never seen it before.
By actually being at these other planets, you can learn so much more and really study them in detail.
Unlike the rocky inner planets of our solar system, Saturn is a gas giant.
It's made from mostly hydrogen and helium, so you couldn't really land on its surface. The gases that compose Saturn are lighter than water, so if you could find a swimming pool big enough and to put Saturn in it, it would float.
Of course, what really makes Saturn stand out from the other planets is its spectacular rings.
So Saturn's rings are very, very thin in comparison to how wide they are. They're very thin, so if you look at them edge on, you can barely see them. And they're made from a mix of things, mostly from ice, water ice, which means that they're very reflective, and that's why we can see them from Earth.
Cassini has also revealed a whole army of moons orbiting around the planet.
We thought that there were about 20 moons, but Cassini's shown us there are at least 60 moons and counting, and these moons are incredible in themselves. They range completely from some that are shaped like potatoes, some that are huge sponges made from, we think, a coral kind of substance. There's one moon, Mimas, that looks like the Death Star, if you've ever watched Star Wars.
But one of the moons in particular caught Cassini's eye, Enceladus. At first glance, it looked like a cold and lifeless, icy body. But then Cassini caught the moon in silhouette, and it revealed something spectacular. Geysers erupting through Enceladus's icy crust, shooting water vapour out into space.
This water vapour has to come from somewhere, so if it is coming from underneath the icy crust, is there a liquid ocean of water underneath? Well, we don't know.
Most of Saturn's moons, including Enceladus, are tiny, but one is a giant, Titan, nearly half the size of the Earth. The moon is covered with a thick atmosphere that shrouded its surface. But Cassini carried a probe built by ESA called Huygens that descended down through the atmosphere and onto the surface of Titan, revealing an intriguing looking landscape.
There's river valleys and dunes, and it's very much like a young Earth. If you could go to Earth 5 billion years ago, this is kind of what Titan looks like now. There's liquid oceans on the surface of Titan, but they're not liquid water, they're liquid methane, and methane's a gas on Earth. But because it's so cold at Titan, so far away from the sun, the gaseous methane on Earth is actually a liquid on Titan.
With spacecraft like Cassini, the distant wonders of our solar system have been brought closer to home. Our planetary neighbourhood now feels that little bit smaller. But we should not forget that sending a spacecraft to another planet is no easy feat.
What I've got here is a scale model of the solar system using different foodstuffs to represent the different planets. Here we have the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. Now this gives you a rough indication of how big the planets are in relation to each other, but it doesn't tell you how far away they are from each other. I really want to show you this because then you'll see how amazing it is that we sent a spacecraft from Earth to Saturn. Now if this was Earth and if Saturn was this big, let me show you where Saturn would really be. I've just passed Mars. There goes Jupiter. It would be here. That's 550 metres on the scale of this line, or in reality, 1.3 billion kilometres. I absolutely love working with the Cassini mission. I've learnt so much in the time that I've been on it. It took 7 years to get to Saturn, but it gives us data every single day. You just don't know what tomorrow is going to bring.
In our solar system, we have a problem, a plague on all our planets and moons.
The inner solar system's like a shooting gallery. It is a clear and present danger.
Craters, impact sites, everywhere you look.
If a big one hits, we all die.
The offenders? Asteroids, lumps of rock, metal, or both. Some older than the Sun. Many from the asteroid belt, a teeming mass of rubble lying between Mars and Jupiter, pieces of a planet that never formed. And comets, remains of the early solar system, lumps of ice and dirt from beyond the planet Neptune.
But the thing about asteroids and comets is that they're small, so they have orbits around the Sun that can change. Now, obviously no orbits are circular, they're all elliptical, but the planets and most of the asteroids and comets have orbits that are very nearly circular. But if you perturb one of those, that ellipse can become much, much more eccentric, much longer and thinner. And that can bring asteroids and comets quite close into the Sun. Now, if that happens, of course, then planets and their moons can get in the way. And that's when we get hit by stuff.
So why does the Earth appear to have no craters? Are we somehow special?
Well, the reason that there appears to be a lack of craters on the Earth is, of course, because of our atmosphere. When a small object hits the top of the atmosphere, then the air resistance slows it right down. The object will either burn up through friction or break up. Well, the atmosphere protects us only from the little ones. Of course, it has absolutely no effect whatsoever on the big ones. But even when you do blow a crater on the Earth, the wind, the rain, erosion, all those weathering processes all combine to wear it away again.
So what would happen if we were hit by a big one?
An asteroid would be hitting the Earth at somewhere between 15 and 20 kilometers per second. When a 10-kilometer sized rock hits the ground, the rock itself simply vaporizes. So what you get is a nice big explosion under the ground. That blows a crater, and if your rock was about 10 kilometers across, you'd expect a crater about 200 kilometers wide. The heat and the blast from the explosion itself is going to take out, well, certainly the area of a large country. The material blown out in that explosion is what really does the damage. You set the sky on fire, which means on the ground underneath, of course, you're under the grill. And it'll also set fire to forests and brushland globally. The smoke and the soot from those brush fires then combine with the dust that was blown out in the atmosphere to simply blanket the planet. Add all of that together and we have a really bad day.
The last time this happened, it wiped out the dinosaurs. Is there anything we can do to avoid the same fate? The first step is to scan the skies for anything that could pose a threat.
But what we're actually looking for, of course, is something that moves. Asteroids look like stars, but because they're members of the solar system, they move relative to stars. Now, what I've got here are 3 images, all of the same bit of sky, but those were taken 2 or 3 minutes apart. And if we get the computer to stitch those 3 together, align all the stars, and then play them back one after another, well, can you see the object move? If you look very closely, that fella there. Once we've found one of these things, then clearly the next thing we need to know is where it's going.
So far, we've discovered many thousands of these near-Earth objects. The majority of them should give us little to worry about, but currently there are over 200 that we have classified as potentially hazardous.
One's called 2004 MN4 Apophis, about 800 meters across, and in 2029 it's going to come exceedingly close to the Earth but not hit it. But the Earth will change its orbit, and we don't know where it's going to go after that. So there is a possibility that it could hit in 2036.
If we were to confirm one was heading our way, then is there anything we could do to stop it?
But once you know what its physical properties are, then you can develop a countermeasure. The first option is to go for the sort of Bruce Willis approach. You know, let's try and blow the thing to bits. All you've done is converted a single, predictable bullet into an unpredictable shotgun blast. The second option is much simpler and much more elegant. All you've got to do is give the thing a tiny little nudge, just enough to guarantee that it misses the Earth. Now, while this is a very rare event, it's the only natural hazard we know of that puts the future of our entire species at risk. But it's the one natural hazard that we can predict, and as we've discussed, we can make it go away.
The orbits of the planets, asteroids and comets around the Sun are not quite circular, but are in fact ellipses with the Sun at one of the foci of the ellipse. To demonstrate ellipses, put a sheet of paper on a corkboard and stick 2 pins close together near the centre of the paper. These 2 pins are the foci of the ellipse. In the solar system's case, one pin represents the Sun and the other is just an arbitrary empty point in space. Tie a piece of string into a small loop and place the loop over the 2 pins. Insert a pen into the loop of string and pull it taut. Draw an ellipse by tracing out around the 2 foci. If the foci are close together, the ellipse will almost be circular, like the orbits of the planets. By making a longer loop of string, you can make a larger ellipse. The orbits of comets are much more eccentric, and so the foci are further apart. Move one of the foci further out and draw the ellipse again. You will notice that this time you get a very different shape. The orbit, like that of a comet, stretches from far away to very close in to the Sun. Here's a way to demonstrate an effect of the Earth's atmosphere. Our atmosphere scatters light and makes the sky appear blue. By shining a light from a ray box through a beaker of water and onto an upright sheet of white card, you can create a beam of light that appears as a sharp vertical line. Then, by adding drops of milk to the water and stirring, you should see that the water starts to turn blue. The liquid in the beaker appears blue for the same reason that the sky appears blue. The fat droplets in the milk scatter the blue wavelengths in the same way that the molecules, like nitrogen in the atmosphere, do. The light shining directly through the beaker onto the card should also now appear orange, just like our Sun appears orange when light from the Sun passes through the atmosphere.